This is a question from AQA A-level Chemistry. It is a paper 3 question based on required practical assessments, and this one is focused on RPA9. I'm going to recommend that you pause, have a go at this for yourself, and then review your answers. So let's take a look at the question. Here are parts A, B, and C. And here are parts D, E, and F. So let's take a look at what we need to do. On the first part, we've got a solution of 4-chlorobutanoic acid titrated with sodium hydroxide solution. The pH was measured after each addition, and we can see how much is added in each case. Small volumes of sodium hydroxide solution were added. The titration data is shown in the table. So we are first of all going to plot the values of pH against the volume of NaOH. What are we looking for here? Well, pH needs to be on the y-axis and volume of NaOH needs to be on the x-axis, and don't forget to include the units. We then need a suitable scale, so you should be using over half of the available space that has been provided. I've done that by going from 0 up to 14 here, and for my volume I'm going across 10, 20 and 30. I'm then going to plot my points in. Now what you've got to be really mindful of here is we have got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 different readings. They are not equidistant. You've got to look at the values. We're going up to 5, then 10, then 15, then 18, then 19, 20, 21, 22, and then they spread out again to 25 and 30. You don't want to fall into that trap of doing them equidistantly. So I put those figures in and I end up with a graph that looks like this. I then need to draw a curve of best fit for these points. There is a very noticeable anomaly. So I am going to not include my 13.32, which is significantly higher, because that would have my pH curve going up and coming back down. You will lose a mark if you do that. On to part C, the pKa of a weak acid is equal to the pH of the solution in which half of the weak acid has been neutralized. Use your graph to calculate a value of Ka for 4-chlorobutanoic acid. I'm going to recommend that you draw the construction lines each time on here. So we're looking for the equivalence point. That's where we've got our steep vertical change, and that is at 20. Now half equivalence happens at half of that volume. So that's going to be 10 cm cubed. So with 10 cm cubed in mind, I'm going to draw construction lines again. I draw in going up at 10 and going across, and that takes me to a pH of around 4.5. From there, H plus is 10 to the negative 4.5. Or pH, is 10 to the negative 4.5. That's going to give me an H plus concentration of 3.98 by 10 to the minus 5. And because at half equivalence we know that Ka is equal to the concentration of H plus, that is also our value for Ka. So our answer is 3.98 by 10 to the minus 5. Let's move on and look at parts D, E and F. Before this titration can take place, the pH probe needs to be calibrated. Outline a simple method for calibrating a pH probe, including any measurements made and how they should be used. So the calibration is the thing that you will have done at the beginning of RPA9, building your calibration curve. And I'm going to go through the basic process that you are hopefully familiar with. First of all, you are going to take a series of buffer solutions of known pH, and you are going to measure with your pH probe the actual value of them. They may be the same, they may be different. But what you're then going to do is plot a graph. You're going to plot the measured pHs against the anticipated pHs of those buffer solutions. And it will probably come out as a straight line graph or close to. You're going to check then, once you've drawn your line of best fit, every pH measurement that you take during your titration, you're going to use the calibration line, the calibration graph, to find out the actual pH. So that is what you would then plot in your results. So let's look at what that looks like in practice. We have our actual pH, the pH that we know the buffer was made to, and we have the pH we actually measured. We plot those points, we draw the line of best fit, and then I measure a pH, and the pH I am going to draw my construction line in. I go up my graph, I go across to the actual pH, and that's the pH that I am going to use when I plot my graph. Moving on to part E, explain how you would use the curve you've plotted in part A to choose a suitable indicator for this titration. So when you think about indicators, indicators change colour, and we are looking for that colour change as the endpoint of that reaction. Now we need that colour change to be rapid. So we need to choose an indicator where the colour change, pH, the pH where it's one colour to the pH it is another colour, is aligned with the steep vertical line on your pH curve. And if I go back to the graph that we're talking about here, we can see a very steep vertical line. You would look at your indicator, and if there was an indicator, for example, where the pH range was 8 to 10, that would work because we can see the steep vertical line aligns with it. But if the pH curve was 6 to 4, it's not going to work because there would be a gradual change in pH over that period of time. We need the colour change to be rapid. Moving on to part F, suggest an improvement a student could make to increase the accuracy of the endpoint when using an indicator in this experiment instead of a pH probe. So when we're using an indicator, we want to add the solution. You'd do this with a pH probe as well, actually. It would improve it. But adding solution dropwise near the endpoint, because pH changes rapidly near the endpoint, and a single drop may well be enough to take you from below the endpoint or below the endpoint pH to beyond. So we would add solution dropwise near the endpoint. That takes us to the end of this question. Thank you for listening and goodbye.